I'm going to back up a little bit just to kind of refresh memories on what we did do last Friday. So last time we looked at finding if we're working at a proportion that we can find the margin of error, how far off we think we are using this formula. Where we're going to take that z-score that gives us the alpha over 2 as our right tail value. P hat is the sample proportion that is successes. Q hat is the proportion of failures divided by the number in our sample. Just goes through the things. The things that had to be met before I could do this to find that confidence interval for my proportion, the sample had to be a simple random sample. The conditions for the binomial distribution had to be satisfied. So there had to be a fixed number of trials. The trials each had to be independent. There's only 2 categories of outcomes. The probabilities remain constant for each trial. We also had to have at least 5 successes and at least 5 failures in our sample. And so we looked at this example where we had the simple random survey of 1,200 residents of Trenton, found that 400 had attended NCMC at some point in their life, and the margin of error that corresponds to a confidence level of 99%. So when we did this one, what did we end up getting for E? I was going to say that sounded really way too high. 0.035? Okay, that sounds better. And so what I was trying to ask if we had done was to find what that range of values were. Now, we already know that P hat was the 400 out of 1,200, which means it was 1/3. So 1/3 is my sample proportion. That's what the sample came out to being. What this margin of error is saying, how far off could it be? And so when we're looking at doing this one, we would take that 1/3 and we might be above or below by this margin of error of 0.035. So what would be my lower limit on my confidence interval? If I took my 1/3 and I subtract 0.035, we're going to get 0.2983. My upper would be 0.3683, would be my confidence interval. That's saying I am 99% confident that the true population proportion of residents of Trenton that have attended NCMC is somewhere between 0.2983 and 0.3683. If my data was anywhere near accurate, it had come from a true sample and was actually relevant information instead of completely made up information. Questions on that one? Another way that you might express this is we would say that 0.2983 is less than the population proportion is less than the 0.3683. So those are saying the same thing. So all 3 of these are ways of expressing that same information. Now, if you express it this way, you'd have to make sure it is P that is in the middle. It's not P hat. It's not the sample proportion. I know what the sample proportion was. Sample proportion was 1/3. But I am trying to use the sample proportion to infer something about the entire population. So instead of having to go through and ask every single NCMC or every single resident of Trenton, then what we would be looking at then is going through and just taking our sample of 1,200 residents of Trenton and using that to infer what we think is true about the entire population. Questions? So this is saying what we were just saying. Another way to express our interval is the sample proportion minus the margin of error is less than the population proportion is less than the sample proportion plus the margin of error. Or again, our margin of error is the same thing. I'm trying to remember if I've got another example before I tell you the calculator shortcut. So we've got 3 common ways to express our confidence interval. So all 3 of these are ways that we have just looked at where we might be talking about that population proportion P has to be between the sample proportion minus the margin of error and the sample proportion plus the margin of error. Yeah, that's what I thought. I don't want to show you guys the calculator shortcut yet. I want to do another one of these by hand. Let's look at number 30 on page 381 or 341. So if we go to page 341 and look at number 30, let me just insert another. So looking at the gender selection, the Genetics and IV Institute conducted a clinical trial of the Y-sort method designed to increase the probability of conceiving a boy. As of this writing, 152 babies were born to parents using the Y-sort method, and 127 of them were boys. What is the best point estimate of the population proportion of boys born to parents using the Y-sort method? What's your best guess? What would we be able to use to have as the best point estimate, the best one value we could say of what we think the proportion of boys would be? That would be what we would anticipate the probability to be. That's if the Y-sort method didn't have any influence. Best point estimate is your sample proportion. So what is my sample proportion? Okay, it's the 127 of them out of 152, which is what is a decimal? Round it to 3 decimal places. Okay. And anytime we're doing proportions, we were back in chapter 2 or 3, chapter 3, we would round them to 3 decimals. I probably should have rounded. Oh, I went out. This one we should have rounded that one to 3 decimals. My stuff went away, so I'm not going to worry about it. So rounding that one to 3 decimals, what's the last? If I rounded it to 4 places, what would it have been? Okay. So we'll probably come back and use that to be able to help us at the end, but I don't have to rewrite it again. Okay, so rounding that to 3 decimals, because when we do sample proportions, we always rounded them to 3 spots. Your best point estimate, the best guess you can have of what you think is true about the population, was your sample proportion. So just from this alone, it's kind of saying that we think that the Y-sort method might be working, because it's definitely a lot higher than that 50% that we would have anticipated being the case if the method wasn't doing anything. Now, if we look at part B, use the sample data to construct a 99% confidence interval estimate of the percentage of boys born to parents using the Y-sort method. So if I want to be 99% confident, that means alpha is what? Okay, it'd be the 1%, so 0.01, which means alpha over 2 would be the 0.005, which means z of alpha over 2. So the z-score that gives me 0.005 in my right tail, so we're looking for the 0.005 in the right tail, which means I want 0.995 in my left tail, 2.575. So that is going to be my z of alpha over 2, is your 2.575. So go ahead and find E. I'm actually going back to the original problem, so I don't have any rounding error. I would, if you were just putting the decimal in, I would do the 0.8355, so you keep those extra decimals. Questions doing that? And make sure you keep those extra parentheses in there as you do things. Once you get that number, the margin of error E, the 0.077, find your confidence interval. So find your lower limit and your upper limit. And if you're not getting the 0.077, please let me know. Don't forget to take it times the 2.575. So when you're taking your lower limit, and when you're doing this one, since you're going to want to round your answer to 3 decimals, I would keep at least 4 decimals in there as you're doing it. So doing at least the 0.8355 minus the 0.0774 gives us what is our lower limit. Okay. So I'm just going to round that to 3 decimals. So keeping 4 decimals as you do the problem so that you can round the final answer to 3 decimals, because you always want to keep at least one more than what the final answer will be, is less than, the true population proportion is less than, and what if we add the margin of error? So our true population proportion is somewhere between 0.758 and 0.913. You could also have written this as an interval of just saying 0.758 and then had the 0.913 and saying that that is my interval of values. Or we could have said it as the 0.836 plus or minus the 0.077. All 3 of those are telling me the same thing. You're right. Most of the time I want them one of these 2 ways. If I ask for the confidence interval, I want to know what my upper and lower bounds are. Sometimes we'll write it this way of some other stuff, but you're right that most of the time I want to know what my interval values are actually going to be. If we go to part C on this, based on the results, does the Y-sort method appear to be effective? Why or why not? What was that? Does the Y-sort method look like it's working? Why? Okay, if there was no effect by the Y-sort method, how many boys would we expect? Half of them. Is this above half? Significantly above half. And so even though that lower limit for the proportion, and we don't know the true population proportions, we're just 99% confident that it's somewhere in there. There is a answer. And that is important to keep in mind as you're doing this. There is one true right answer for what the true population proportion of boys would be based off this method. Boys born using this method, I guess I should say. There is one true population proportion. We're just saying, okay, based off my sample that we have, this is my best estimate, is that it's somewhere in here. So it may be the 0.758, it may be 0.913, or it could be any number in between. But we're 99% confident it's in there somewhere. Now, from that, even since our lower limit is significantly above the 50%, it looks like this method's having an effect. Can't guarantee that you're going to have a boy, but it's highly increasing your probability of having a boy. Now, let's look at how the calculators can help you. I want you guys capable of doing these, and I will probably ask for you to do a problem by hand where you have to go through and find the margin of error by hand. So you need to know how to do these things by hand and probably practice some of them on the calculator, or practice some of them on the homework doing them by hand. But the calculator can do it for you. A lot of what you also have to know is once you get your information, what did you just find? That's a lot of what you're trying to do. To find my confidence interval, though, I'm going to go to statistics, arrow over to tests. We are selecting the very first one, a 1 proportion Z interval. So we are dealing with having just one proportion that we have, one value that you're working with. You don't have more than one thing that you're working with. You're going to use the Z-scores when you're doing these. So you're doing a 1 proportion Z interval. You're going to put your X value, which was the number of successes, N, which was the sample size, your confidence level, so if we want to be 99% confident or 90% confident or 95% confident, then you're going to go to calculate. So for the very first problem that we did, where we were looking at the number of Trenton residents that had gone to NCMC from my made-up data, and we wanted to be 99% confident, we would do the 1 proportion Z interval. My X value was the 400 people that were NCMC, had gone to NCMC. The 1,200 people that were my sample, my confidence level was the 0.99. Yep. Oh, you're doing Z-test, not Z-interval. So go to stat, arrow over to tests, and you want to go down further. It's number 7. No, it's not. Keep the arrow in. Where's 1 proportion Z? It's number A. Yeah. You are actually trying to jump ahead to what we'll do in Chapter 8, where we're going to have a test that we are saying we think it's going to be this. And okay, is everybody finding it? So you have to go clear down to A. Okay, yeah, you're good. Well, why do you hit enter twice? Wait, no, stop that. Hit clear. Okay, go down to calculate. Hit enter. And it did it. No. Calculate is doing the enter. Because you were hitting it so fast that you didn't even see the answer pop up. All right. Using the calculator on this one, what would go where? No. No? So I've ruled out the 0.836 and I've ruled out the 152. So 127 is the piece that's left that we haven't gone with. So X is the number of successes. It's not the proportion of successes. It is the number of successes. N is what in this case? 152. And what is our confidence level? We want to be 99% confident. You should have the same answer we had before, 0.758 to 0.913. You're good. Okay, now I'm curious. If you hit enter again, which, yeah, it doesn't let it do that. Okay. Nope, I was wrong. I was thinking I would be able to fix it, but it won't. Okay. Now, we're getting that same confidence interval, and it's giving us this value that we had before. Just out of curiosity, what if we change this to not being so confident? If we change this to a confidence level of 90%. First question, before you even start doing it, just from what you think you know, would you expect the confidence interval to get wider or to get skinnier? Because? No, I'm asking. I'm not telling you you're right or wrong because I don't want to tell you ahead of time. Okay? So if you're allowing for more room for error, you're going to be, you're allowing it to be less confident. So stick with explain to me why that means it's going to be bigger. Okay. So we're going to go and just look at it. We'll get there in a second. Anybody else have an opinion? Let me ask, I'm going to make you all vote because I'm curious how many of you vote which way. How many of you guys are going to go with these guys if thinking it's going to get wider? How many are going to go vote against them and say it's going to get skinnier? You guys have to vote. You got a 50-50 guess. So 50-50 guess. How many people are going to vote with them and say it's going to get wider? How many are voting against them and saying it gets skinnier? Now I want you guys to find out if you're right or wrong. Because I didn't let you. So everything else is staying the same except for the confidence level is going to go to 90% confident. So what'd you get? Someone be both. First of all, let's look at what our numbers were. What's our lower bound? What's our upper bound? Okay. Now, why did my confidence interval get skinnier instead of wider? Let's look back at what we do think we know. If we're 99% confident, then we're only allowing a 0.5% in each tail. If, on the other hand, I'm wanting to be 90% confident, different color, 90% confident means that I'm allowing 10% between the two tails, which means each tail has 5%. Will the z-score of z of alpha over 2, will that be a bigger number or a smaller number? It's going to be smaller. Because, I guess I didn't line things up very well. Let's make it a little wider here. It's going to be a smaller number because we're allowing more on the ends. We're not going out to being having a tiny bit of extremes. We're allowing more on those extremes on both ends. Now, if I'm allowing myself to be wrong more, 99% confident, I'm saying I am pretty darn sure that the true proportion somewhere between these two values. Now, 99% confident between 90% confident. 90% confident says, I'm pretty sure, but I'm allowing a pretty substantial extremes that could happen that might accidentally be outside of what I'm allowing it to happen because I'm only 90% confident. If I'm allowing myself to only be 90% confident, I'm allowing for more error, more times that I could be wrong, is really what you're looking at. And so if I'm allowing for more chances to be wrong, my interval is not going to be as extreme. Because I'm not trying to capture all of those true extremes that are out there. So I'm looking at, if I put everything on one picture, probably make it easier. Let me start over with a new picture, make it all just in one spot. No, not unless you do the entire population. Because you always stand a chance of something that's just way out there so extreme that you can't think about it happening. Now, we can get close to that, but without doing the entire population with statistics, we don't allow for that to be a possibility. Okay, so we're saying for the first one that we're only allowing the 0.005 as our outside. So this was the z of 0.005, which was our 2.575. If, on the other hand, for the second one, we're saying, okay, so we don't want to be as confident, we're going to be 90% confident, then this is doing the z of 0.05. I'm allowing 5% to be in that outer tail and 5% in the lower tail. And so you're not going to be as confident. You're saying, okay, so I'm going to have, and what this is really saying is, I'm 90% confident they're between these two values. I'm 99% confident they're between these two values. And so you're getting more confidence because you're taking away some of those extremes, you're adding them into what you already have. So as you get to be more confident, your intervals are going to get wider because you're capturing more of those extremes that are just happening way out there on the outside edges. All right, round off rule, I've mentioned this one already. Round the confidence interval limits for proportions to 3 significant decimal places, and that's because when we find proportions back in Chapter 3, we rounded those to 3 significant digits. So as you deal with proportions, we're going to continue just to round them to 3 significant digits. When analyzing polls, things to think about. Consider the sample should be a simple random sample, not an inappropriate sample such as a voluntary response sample. So when you listen to politics and they start looking at, 40% of Americans support blah, 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 and then they'll say plus or minus 2%. That plus or minus 2% is their margin of error that they're allowing for. So based off their sample size and all this type stuff, well, one thing that they need to make sure of is they came from a good, simple, random sample. And so a lot of those, like Gallup poll and stuff like that, make sure they get good, simple, random samples. But on the other hand, if your news just had this little, call us if you have an opinion, call us if you support blah, whatever, whatever, well, then you can't take that and make a good confidence interval out of that because you're not guaranteed that you had good data. If it's a voluntary response sample like we talked about back in Chapter 2, I might call if I've got a really extreme opinion, but if I'm just a middle of the road, could care less, probably not going to waste my time to call. And so you've got to make sure you've got good data. It can't be a nice little, convenience sample of the first 10 people that walked by me type thing. I know I have you guys, can't remember if it's Chapter 7 or Chapter 8 project. I have you guys conduct a sample. I don't force you to have a good, simple, random sample, and most of you do convenience. I've had a lot of people that are, based off the first 20 people that responded on Facebook, my opinions are, and definitely not a good, simple, random sample when it's convenient and voluntary both at the same time. So looking at those are definitely things to consider as you do these. And especially when you're trying to read polls that you're getting information out of resources from. Also, the confidence level should be provided. Most of the time, the confidence level that's given is 95% confident. Media reports often neglect to identify that when you look at it. A lot of times 95% confidence level is what you do. If they really want to be confident about things, they'll go out to 99% confident. If they're allowing themselves a little bit more wiggle room, they'll go down to 90% confidence. The sample size should be provided. It usually is, but sometimes they leave those out also. And we're going to look, actually I think here in just a second, we're going to look at how big is big enough for our sample sizes to be able to make any kind of conclusions from things. Except for relatively rare cases, the quality of the poll results depends on the sampling method and the size of the sample, but the size of the population usually isn't a factor. So when I'm trying to decide if I want to be 90% confident and I'm making sure I've got a good, simple, random sample, trying to figure out what the sample size is, how big that sample population needs to be, I really don't have to pay attention to whether I'm doing the sample for NCMC, the town of Trenton, the state of Missouri, the United States population. Sample size will actually be pretty much the exact same for all of those. So what that sample size needs to be does not depend on the population size, but it does depend upon the size of how perfect or how good I want my sample to be, what my confidence level needs to be. So, trying to figure out how big is big enough. If we look at what we had, what I want to do is figure out what does that value need to be? What does that sample size need to be for this problem? If we're trying to solve this, so just doing a little bit of algebra together, what would I do to get n by itself? Before I square it, get rid of this guy first. So we'll have to divide by z. Now, as you guys said, we would square both sides. And so we'll have e over z squared is p hat q hat over n. Then what? Okay, I gotta get n out of the bottom. Well, if I want to get n out of the bottom, what I can do is just flip both sides. Because I could multiply by n and then divide this, and it's just flipping both sides. I'm trying to remember what my final answer ends up looking like without looking at it. Might be the same thing. So now what? Okay, so we'll have the p hat, q hat times my z over e quantity squared equals n. Is that the way they end up writing it? Ooh. Yeah. So what all I did differently is they squared both of these separately, and so you have p hat, q hat times z squared over e squared. So, needless to say, not a thing I'm going to make you do every single time when you're getting to rearrange these equations and solve for it. But that's all it's doing. It's the exact same formula, just rearranging that formula and solving for n instead. And so if I wanted to know how big is big enough, the things that matter is what am I allowing my margin of error? Do I want to be off by 3%? Do I want to be having a possibility of being off by 5%? What is that margin of error? What's my confidence level? Do I want to be 90% confident, 95% confident, 99% confident? P hat and Q hat, if they are known, we'll put those in there. So if I already have done, for example, when you get close to elections, they will be almost every single week saying, okay, so for the presidential campaign, that today, 90, or no, it would never be that high, 54% of the people were supporting Obama. So if we went back to the last election, 54% of the people are supporting Obama. Well, next week when we go back to redo it again, We already know that last week it was 54%. It probably has not had a significant jump unless something serious happened that all of a sudden, one politician's campaign just plummets. More than likely, you're not going to have this huge jump from one week to the next week. P hat and Q hat are pretty well already known. So you can just use them to estimate what that sample size needs to be. If, on the other hand, we have no clue, I've never gone out and researched how many college students would like to see McDonald's on campus. Never have researched that, don't have any clue what would be the proportion of people, then I've got to take the worst case scenario. Worst case, and I've just totally made up something so I can see you two are over here thinking about it. I'm not asking for your opinion because it's not in discussions. Worst case scenario, what would be the largest number that we could put in for P hat and Q hat that when we multiply them give me the biggest value? Use your calculators and figure that out for me. What would be the biggest numbers? Now, what do P hat and Q hat have to add up to be? They have to add up to be 1. Aaron, what was your guess? 50%. If you take 0.5 times 0.5, you get 0.25. Is there anything else I can multiply by and get something bigger than 0.25? If I took 0.4 and 0.6, you get 0.24. Anything else you're going to multiply together is going to give you a smaller product out of this. So my worst case scenario is if I put in 0.5 times 0.5 and I get 0.25. Now, why do I want worst case scenario? Worst case scenario is going to give me my biggest sample size. If I am actually conducting a sample, I'd much rather interview 100 people than I would have to interview 200 people. So keeping my sample size the smallest possible, definitely going to be what you're aiming for. But you've got to make sure it's big enough that it's a good enough sample size that you're not just wasting your time doing it entirely. If I came up here and I decided that I needed to have 125 in my sample and I only interviewed 100, then I've wasted my time and I got to start all over of getting myself a good simple random survey. And so you've got to make sure that you've got a sample size that's large enough. So these are going to be the ways we calculate these. Notice also those are both on that reference guide. You do not have to memorize either one of these. So just understand that if you know the sample proportion, if I knew that it was 52%, then what is 0.52 times 0.48? Okay, so it's giving you something that's a little smaller than that 0.25. Well, when I multiply that by the z over alpha squared divided by the margin of error squared, it's going to have an impact on my sample size. Also, I guess I also wanted to point out here, notice again, nothing in here had anything to do with population size. So whether I'm interviewing the college campus, the entire town of Trenton, the entire state of Missouri, the entire population of the United States, it doesn't make a difference on how big the sample size is. Our round-off rule. If I am trying to figure out how many people I need to interview or how many M&Ms I need to sample, or if we're at a product line, if those type of things are what we're looking at for the sample size, what would make sense for the round-off rule? You need to go to a whole number. Now, if I'm talking about a sample, would I rather have too many or too few? I'd rather have too many in my sample size, so always round up. It doesn't matter how small it is. If I end up getting an answer that is 124.01, because it's a little bit more than 124, you have to round that up to 125 in the sample. Your sample size always has to be a whole number, and you want it as big or bigger, so you will always round those values up. Because you'd rather have too many in your sample than not enough in the sample, because if there's not enough in the sample, everything gets thrown out, and it just wasted useless information. So if we look at an example, if we look at number 44 on page 343, Name recognition. As this book was being written, former New York City Mayor Rudolph Giuliani announced that he was a candidate for the presidency of the United States. If you are a campaign worker and need to determine the percentage of people that recognize his name, how many people must you survey to estimate that percentage? Assume that you want to be 95% confident and the sample percentage is in error by no more than 2 percentage points, and also assume that a recent survey indicates that Giuliani's name is recognized by 10% of all adults. So, first question, am I using the top or the bottom formula? No. Why the top? Okay, because we know that about 10% of people already recognize his values. I want to be 95% confident, so what is Z of alpha over 2 for 95% confident? So my alpha is going to be 0.05, which means alpha over 2 is 0.025. So what is Z of 0.025? So you're looking for the 0.975. Do the positive, 1.96, because you're looking for the 0.975. Okay, so 1.96. Don't forget to square this. What is p hat? That is your 10%, because we're assuming that we know that it was about, the last time we did the survey, it was 10% recognized him. So what is q hat? Okay, it's going to be your 90%. What is my margin of error? I want to be wrong by no more than? Be wrong by no more than 2%. I want this to be a plus or minus 2%, which is what you see most of the time when you do these kind of surveys. So that's going to be the 0.02 squared. And again, don't forget the squared. And so then what do you guys get? What was the actual number? 860 what? So if we're getting 864.36, everybody getting that? If you're not, please let me know. Which means we're going to round this to what? We need to have 865 people interviewed to make sure that we have a sample size or sample that's good enough to be able to use it. You can, yeah, you can do extra. Mm-hmm. Actually, when you go up to higher amounts, it'll probably change your margin of error to being a little bit, instead of being plus or minus 2%, you actually be off more like plus or minus 1.9% or something like that. Yeah. Then again, when you're doing this and you're going to have to do all of the data crunching for them, 865 might look a little bit better. All right. Now, when your guys' calculators gave you the information, your calculator gave you your upper limit and your lower limit. If I had done something and I had my calculator tell me that the margin of error was going to be 0.246 to 0.384. If that's the margin of error that my calculator, or my confidence interval that my calculator gave me, and I really wanted to know what was the sample proportion and what was the margin of error, I want to write this instead as p hat plus or minus e. How do I get there? Well, if I know my lower and my upper limit, where is the sample proportion at in this interval? Smack dab in the middle. How do I find smack dab in the middle? Add them and divide by 2. And so if I did that, if I added those two numbers up and divided by 2, I end up getting 0.315. That is my sample proportion. If I want to know my margin of error, what is that amount that I can add on or subtract from this to figure out my extremes, then I want to know what's the difference between those two extremes. How far have I added and subtracted? And I want to cut that in half because half of it was added to go above, half of it was added to go below. Now, when you do this one, be careful. You put things in the right order. You want the bigger number minus the smaller number. So you do upper limit minus the lower limit. So you take the 0.384, subtract the 0.246, take that answer and divide it by 2 to get that we're getting 0.069. So instead of expressing this as 0.246 to 3.84, I can say this is 0.315 plus or minus 0.069. That those two things are saying the exact same information. So it's just different ways to express it and understanding what you're doing. If you take 0.315 plus 0.069, you better get 0.384. If you take the 0.315 minus the 0.069, you better get 0.246 because they're expressing the same things. Oh, I had an example. Okay. There's your guys' homework. On Wednesday, we will be doing section 7.3, which will be doing the same kinds of ideas, only talking about the mean when we know the standard deviation of the population. And then it'll also still get to use the z-scores. Next week, we'll talk about same confidence intervals for the mean when we don't know the population standard deviation and for standard deviation. Those will use different test statistics instead.